Hello, everyone. My name's Patrycja Wegrzynowicz, and today I'm going to tell you about multi-cloud connectivity across three clouds: AWS, GCP, and Azure. Briefly about myself, I've been doing professional software development for over 20 years. Software development was my first love, but last year, I joined the dark side and became platform engineer at Form3. I've been working on multi-cloud connectivity to support our payment platform. Now I'm lead engineer working on reliability and performance of UK payments. Briefly, our agenda, what am I gonna talk about today? Why do we need multi-cloud connectivity at all? Then this will be followed up by demo, which I would like to show you to the end goal of our system. I will explain connectivity options across several clouds. I will talk briefly about Kubernetes and CNI, and then I will show you our performance results. Why do we need multi-cloud connectivity? To start with, it's good to explain Form3 background. Form3 is a UK-based company which provides a payment platform for financial institutions. So basically, we provide a simplified API to integrate easily with multiple payment schemas like SEPA, SWIFT, FPS, etc. So this way, our clients can integrate with those schemas more easily and quickly, thus saving time and money. We are a very technology-oriented company. We are cloud-based. At the moment, our production system is based on AWS. Our components are, and our architecture is based on microservices written in Go and Java. And we take infrastructure as code almost religiously. We terraform everything what's possible and even more. So first, the challenges of payment processing. So basically, you can understand when it comes to payment, we first and foremost need reliability and durability. So usually we have some contractual obligations and we need to provide specific SLAs to our customers. And any outages and errors must be handled without any loss of data. That's super important. So then when it comes to volumes, you can imagine that when we are talking about payment platform for many several banks that serve millions of customers, it means huge amount of transactions with a virtually unlimited number of users. And on the other hand, we have payment schemes. And when it comes to payment schemes like SWIFT, SEPA, and others, it's very difficult for us. They keep changing. They keep updating. And such updates are very difficult to keep up to date when you have a small team in a single bank. That's why Form3 provides this integration platform and makes this integration easier. On the other hand, it's a challenge for us that we need to keep our releases on time without any disruptions, etc. So, so that's why we invest in cloud and multi-cloud, especially when you take a look at last year top cloud outages. Here you can see top 7 outages in 2021. That's according to techgenics.com. And you can see outages among major cloud players like Amazon, Google, Microsoft, etc. So I'm pretty sure that most of you were hit by one or more of those outages in the past. Myself, I was hit by the number 4 when Google Cloud Network resulted in 404 error. Basically, I had a Discord server because for my students, I also teach at Warsaw University, and for my students, we had like Discord server, and we couldn't do exercises that time because Google Network together with Discord went down. So that's why the answer is to go multi-cloud. At Form 3, we are working on new payment platform with those very high availability, feature, resiliency, scalability, and performance needs, together with security. We've decided to use AWS, GCP, and Azure. And our technology stack includes cloud-agnostic tools which can be deployed in any of those clouds. It includes Kubernetes, NATS, and CockroachDB. NATS and CockroachDB in clustered mode across 3 clouds. Our goal is to have like a resilient failover across 3 clouds. So whenever one of the clouds goes down, the service can switch and reach another cloud. That's why we are going to use Cilium as our CNI. And together with Cilium, we have Cilium cluster mesh availability feature, which provides global service. And this global service across 3 Kubernetes clusters deployed in each of the clouds can provide us with this silent failover. Now I'm gonna show you a small version on my personal accounts. That's a Star Wars demo prepared by Azure, the company behind Cilium. And in this Star Wars demo, we basically see how global services work, and we see failover in action. So I've prepared 3 clusters. The first one is in AWS. The second one is in GCP, and the third one is in GCP as well. We have X-Wing and Rebel Base deployments in all 3 clusters. Now I will board my X-Wing. And I will try to reach Rebel Base from there. Oops. Some connection problems. Okay, we are here. Okay, now I will try to reach my Rebel Base service. Okay, we got it. And now I would like, that's deployed as global service. So at the moment, we've got the answer from the cluster 1, but I would like to hit it many times, so to see the answers from other clusters as well. So a short bash script to hit Rebel Base thousands of times with a short sleep, and we are done, I think. Okay, so we see that we are getting at the moment the answers from GCP clusters, but basically we see the answers from all three clusters. So what happens now? I will scale down. I will scale down one of my deployments. That's cluster. That's the second cluster, the first one in GCP. So I will scale it down to 0 replicas, and we should see that the answer in a moment when the termination will take place, we will see only the answers from 2 clusters. Sometimes there is a hiccup, or the refresh takes a couple of seconds or even a minute. The other problem is related to connectivity, because as I told you, I'm using my personal accounts, and with my personal accounts, I use VPN as connectivity option. So a VPN, as you see, has some hiccups sometimes, and it's not as reliable as other options. And I'm gonna show you that later on. So yes, we see only the responses from 2 clusters now, and let's switch to our third cluster and let's scale it down as well. So the last cluster has been scaled down, and now we see only the responses from our AWS cluster, and now Form 3 rules the galaxy. But we are not that greedy, so I'm scaling back our third cluster, and we should see GCP cluster 3 responding as well. So that's our goal, to have like seamless failover across multiple clouds. How can we achieve that? First, we need to connect our 3 clouds in reliable and fast way. So when it comes to requirements, obviously, when we talk about clustering of CockroachDB and NATS, we need pretty low latency. So connectivity being fast was our main requirement. Other than that, we have very, very high, I would say even insanely high requirements when it comes to reliability and security. And obviously, we want to get things done, so we need that safe landing, and we need to make sure that our approach is actually feasible. So when it comes to detailed requirements, we focused only on one region. So 3 clouds, but only in one region. In our first release, we wanted to focus on London region. Our latency should be lower than 5 milliseconds across clouds. We need steady bandwidth. We need connection to be secure or private, preferably. Obviously, we need high availability and fault tolerance in case of failure on any level, being it a link, device, or a cloud point of presence. So when we discussed connectivity options, we came up with 3 connectivity options. The first one was virtual private network across clouds. The second one was direct connectivity via cloud exchange provider. And the third one was direct connectivity via data center. With VPN, the advantage is that basically VPN is an encrypted tunnel over the public internet. Each packet before transmission is encrypted and then sent to the other part. The advantage of this option is that it's basically available out of the box for all three major cloud providers, which were the interest of us. The second option, direct connectivity via cloud exchange provider, we basically use network as a service provider. So some third-party vendor which allows us to quickly create direct connections across clouds, namely Direct Connect, Interconnect, or Express Route for respectively AWS, GCP, and Azure. And then having those three connections to three clouds, we can use the virtual router, which routes traffic across those three connections. Then the last option is a very similar one to the second one, direct connectivity, but without third-party vendor. So instead of using cloud exchange provider company, we have our own data center or rented the data center, and we have direct connectivity with three connections like Direct Connect, Interconnect, and Express Route. But instead of virtual router, we use a physical router in a data center. So let's dive into those three connectivity options with pros and cons for them. So basically for VPN, as I told you, it's the solution which is available out of the box for all three cloud providers, even with high availability setup. The other very important advantage for us was that infrastructure as code is possible. As I told you, we use Terraform and we use them for all our cloud resources. So it's a very important point for us to have a Terraform provider and terraforming the solution. Another good point is that no third-party dependency is required, so less dependencies. Usually it means that the solution is quicker to implement and easier to maintain. On the cons side, on the other hand, there is that our traffic goes through public internet. What does it mean for us? It means basically higher and unpredictable latency. So even though we can have like pretty good latency on average, there are some spikes with high latency. Another thing is unpredictable bandwidth. So even though we have like outbound and inbound rates guaranteed, once it goes to public internet, you never know what happens. Another thing, especially important for a fintech company, is unpredictable routing. In many countries, you have special regulation to where your data, in which country they can be stored. So, for example, in European Union, it may be that they can't cross the borders of European Union, and some similar regulations in other countries as well. So with public internet, you have unpredictable routing. You don't control it, so you don't control the way your packets go. So it can cross borders, basically. So that's also downside for us. And last but not least is it would be more difficult to configure failover once we wanted to combine VPN with other solution. With direct connectivity via Cloud Exchange provider, we did our research and found a couple of viable companies for us, namely Megaport, Equinix, Unitas, Aviatrix, and there are many more out there. We focused on Megaport because they have pretty good presence in many countries, especially also in London region. So we did our proof of concept with Megaport. And another important thing for Megaport was that it provided Terraform provider, so we could Terraform our infrastructure. So that's definitely one of the pros. Infrastructure as code possible, but not for all the providers, only a few of them, and Megaport being one of them. We have very good predictable latency, very good dedicated bandwidth, because basically we use direct connectivity across clouds, and we have virtual router. So underneath there must be some physical router, maybe shared router, but in some physical data center in a given region. We have obviously secure private connectivity, so definitely those points were met, and very good with Megaport. On the other hand, Megaport have limited presence in different regions. Basically, cloud exchange providers have a limited presence in different regions. So depending on the region, you could use like different cloud exchange provider. We need to, for ourselves, we need to think about the future. We are expanding to US markets, so we are looking at US US presence as well. And with Megaport, even in London region, we had some problems with high availability option, because the first link was directly in London region, but the second link, redundant link, was routed via Frankfurt. So the latency was unacceptable for us. As far as I know, that's changed, and now Megaport provides redundant links in London region as well, but you can see that it may vary from cloud exchange provider to cloud exchange provider, from region to another region. Another problem was audit requirements. As I told you, we have some contractual obligations with our financial customers. So part of them is very high audit requirements. All our infrastructure must be audited, including our third-party vendors. So with Megaport, it was difficult to meet those audit requirements. And so with Megaport, it was difficult for us to get enterprise class support. So for our production systems, it's like a must in fintech industry. So then we investigated and tested our direct connectivity option via data center. Obviously, this one had very good predictable latency under 5 milliseconds, together with good dedicated bandwidth. Depending on our needs, we can configure different connections with different bandwidth to all three cloud providers. We also have flexibility to choose different cloud connections and different cloud exchange providers per region, so that's always a plus. Unfortunately, for us, the big downside was that infrastructure as code was not fully possible. Why? Because we have some third-party vendor which takes care of our data centers and our hardware in data centers, configuring all our physical hardware and physical routers, and they don't support and then they don't use Terraform. However, I think they are thinking about switching to Terraform, so maybe in a short future that would be possible for us. However, at the time of our research, that was not fully possible. So once you don't have this automation and you need to do manual actions on your routers, it takes longer. It takes longer, especially when you think about production systems, when you need to have like a maintenance window in one of your data centers to do your maintenance work and updates. Moreover, we have limited monitoring and observability options here, as those are hosted connections and data center routers when we don't have full automation. And those are managed directly by our third-party vendor. In the end, we've decided to use, even though there are significant drawbacks, we decided to use direct connectivity via the data center. Basically, our main motivators were good predictable latency for redundant connections. So with Megaport, we couldn't achieve that. Then audit requirements. Our vendor has been audited, and that's one of our contractual obligations. So that was technically the most viable option for us, as well as from the legal point of view. Here you can see high-level design of our connections. We have 3 clouds. We have 2 data centers. In data centers, we have 2 routers. In each of the data centers, we have 2 routers, and those 2 routers have connections to each of the cloud, redundant connections to each of the clouds. How does it look like in detail? So basically, we can take a look at each cloud because those configurations are slightly different. So basically, as I told you, we have redundant connections to each of the data centers. So we have connection 1 primary and secondary for DC1 and connection 2 primary and secondary for DC2. In AWS, this is related to those connections are configured on virtual interfaces. So we have 4 virtual interfaces. Those virtual interfaces are connected to Direct Connect Gateway, which is attached to Transit Gateway. And our virtual private clouds, our VPCs, each of them is attached as a Transit Gateway attachment to the specific Transit Gateway. In case of GCP, we have also redundant connections to DC1 and DC2, but instead GCP doesn't support such concept as Transit Gateway in AWS. So instead, they recommend to use transit network with cloud router. So we need to configure a specific virtual network which serves as a transit network. In this network, there is a cloud router, and our virtual networks which correspond to virtual private cloud in AWS. So basically the same concept of virtual network. So those VPCs, VNets, they are paired to our transit network, thus having possibility to route through our cloud router and then to specific cloud. In Azure, again, express route connections, redundant and similar to GCP and AWS. However, again, the routing is configured a little bit differently, and we have different concepts in each cloud. So in Azure, we have virtual one with virtual hub. Express route gateway is attached to virtual hub, and to the same virtual hub in virtual one, we have attached virtual networks. So that's how it looks like from Azure point of view. And for routing, we use border gateway protocol. This is basically a protocol to exchange routes dynamically. We need to take into account different BGP configurations and limits in each of the cloud. Each cloud supports a little bit different limits for allowed prefixes to be advertised. The problem, the biggest problem was in Azure, because AWS and GCP, they support advertisement of custom routes. So basically, if we want to advertise and be available VPC1, VPCB, VPCC in AWS to be advertised to other clouds, we can do it by advertising each prefix of the network separately, or we can create an aggregate prefix. In case of aggregate prefix, it's easier because we advertise only one aggregate big prefix, and this way we avoid and we are within the limits of BGP advertisements. However, those custom routes are not available in Azure. So we couldn't create aggregate route in Azure. Therefore, we needed to change the configuration of our routers and to accept or longer match instead of exact match in our data center routers. Why we want to have aggregate prefix? Because this way we have more flexibility in network design in each cloud. So we don't need to change anything in our routers once we add or remove one of the VPCs in any of the cloud. In case of failover, we designed this with active passive mode to avoid overutilization of links, and this is implemented based on priorities, latencies, and BGP multi-exit discriminator. So basically the configuration depends and is supported in each cloud. Active configuration could be possible as well. However, we don't want it for our connection links because in case of a failure of one of the link, it could happen that we don't have enough bandwidth. So in such cases, it's better to configure it as active passive. But that's the beginning, because that's the beginning of our cloud configuration, because we need to make our networking configuration secure. So we need to focus on such concepts as network segmentation. For example, if we only want to connect VPC-A to respective VPC-As in other clouds, it means that we need some sort of network segmentation. We need to block traffic to other VPCs. Considering that we need to implement defense in depth principle, we can't rely only one control mechanism. So, for example, it's not enough to use security groups or firewall rules, because that's only one security mechanism. In addition to those security groups, firewalls, we also need to configure correct routing with least privileged network principle in mind. And that's not that simple as it sounds, because again, we have very different networking concepts in AWS, GCP, and Azure. So with AWS default configuration, we have default transit gateway route table. And this means that basically VPCs can route to any other VPC connected to this transit gateway. The answer to the problem is to use a separate transit gateway route table per VPC. In GCP, the problem was even bigger. As I explained to you, we used network peering between our VPCs or virtual networks, as they are named in GCP, and our transit network. And the problem is that with network peering, you can't filter dynamic routes. That's like all or nothing approach. And we can't have static routes pointing to peering connection or cloud router. That's just the way networking is designed in GCP. So the answer is pretty convoluted and complex. The answer is to use HA VPN between GCP networks over BGP. So inside GCP, we use HA VPN, and they provide guarantees that the traffic won't go over public internet if both sides of HA VPN reside in GCP. So in similar problem was with Azure Virtual Hub. Virtual Hub basically provides full mesh features. So once you are connected to Virtual Hub, you are visible and you see everything what's connected to this Virtual Hub. So again, the answer might be HA VPN between Azure VNets, but that's something we need to look into further. About performance tests. So when it comes to performance tests, we've used very cool K8s NetPerf deployment. It allows to test Kubernetes performance based on iPerf, NetPerf, and Fortio. The most important numbers for us were from NetPerf with TCP request response test and TCP connect request response test. So those are the most important to us. And when it comes to latency for VPN, When you take a look at VPN and node-to-node versus pod-to-pod connectivity, you don't see so much difference. That's good. And actually, the average, for example, P90, 90 percentile of latency latency is pretty good. Here you see results for each pair of the cloud. That's for node to node, and this one is for pod to pod. There is no difference between node to node and pod to pod. That's good. So it means that Kubernetes overlay network doesn't provide, doesn't introduce overhead. We see that respective latencies are in line, so that's good that Kubernetes is not a problem for us. But when you compare VPN and DC, you see that obviously connectivity via direct connectivity via DC via data centers is faster, but it's not that much faster. It's however, P99 here, we can see big difference for AWS GCP, basically for most of the pairs. Here we have like the least difference for GCP Azure, but for example, AWS and GCP, P95 is twice as fast for direct connectivity. So basically, it means that this connection is more stable and more reliable. So we don't have those unexpected spikes which can happen when traffic goes over public internet. This is one of very interesting tests. Basically, here we have like skyrocketing spike when it comes to VPN multi-cloud connectivity for GCP Azure. So you can see that P90 is like 60 milliseconds. So completely unacceptable for us. But that was kind of anomaly. On average, you get much better results. But again, for production system, you don't want to have those anomalies. Thus, VPN is not the best solution when you need low latency. In terms of VPN, comparing VPN and DC, we've seen similar one before. And basically, let's focus on P99, and P99 is twice as long as direct connectivity for VPN. So for VPN, we have around 5 to 6 milliseconds latency across clouds, and for direct connectivity, we have 5 milliseconds. For VPN, we have over 10 milliseconds, hitting over 12 milliseconds for GCP and Azure VPN connectivity. When it comes to Kubernetes CNI, it's important so basically, we don't have much time to go into details of Kubernetes networking model. However, I would like to highlight some issues here. I mentioned that we use Kubernetes, and I mentioned CNI here. So basically, when it comes to Kubernetes network model, we have this model when we have IP per pod concept. Every pod gets its own unique cluster-wide IP address, and pods can communicate with all other pods. That's very important. Kubernetes provides some sort of overlay network over host network. So usually it introduces some overhead. When it comes to Kubernetes and networking, the important term is container network interface, CNI. When the CNI, that's like a framework to configure networking resources for containers. And this framework is plugin oriented. So basically, to provide networking capabilities for Kubernetes clusters, we need to provide a CNI. CNI plugin is required to implement Kubernetes networking model, and we have different CNI plugins. Each cloud provides in its managed Kubernetes clusters their own CNI plugins, like AWS CNI plugin, Google and Azure. They provide custom CNI plugins, but also we can use generic generic plugins like Calico, Cilium, Flannel, or Weave. As you've seen during my demo, I've used Cilium there. Cilium has this feature of creating a cluster mesh and providing global service. That's why we decided to use Cilium. However, in practice, it turns out that it might not be the best choice. As always, the answer in IT is it depends. It depends on your specific use case and specific requirements. Basically, Cilium advertises itself as a very fast CNI plugin, operate using eBPF, so some sort of dynamic insertions directly into Linux kernel. So instead of IP tables, they use like routing based on this inserted code. So it's supposed to be much, much faster than IP tables, because with IP tables and large chains inside IP tables, you have a problem of linear search. So basically, the more pods you have, the slower your routing is. However, in Cilium, the problem is that in clouds, they have kind of limited capabilities when it comes to using eBPF. And for example, they still use host legacy routing, and it's not available to enable this eBPF routing on host level for any of the clouds. That's because networking in clouds is different. And is different than in a custom data center when you have full control over your infrastructure and hardware. When you compare Cilium to cloud-native CNIs plugins, you don't see so much difference across clouds. So for each pair, the results are pretty similar, even in some cases, on average for P50 or P90, the performance of native CNI plugins is better than Cilium, but in general, it's very similar. So you don't get much of the performance gains with Cilium. On the other hand, you can get much more in terms of functionality. For example, more advanced network policies, or if you are focused on encryption. That's what Cilium can provide out of the box. So when it comes to multi-cloud networking, you see that's not as simple as you could imagine. At least at first, our impression at Form3 was that it was gonna be much simpler than it turned out. We have a lot of connectivity options to navigate across them. It's not that easy. You need to be an expert in each cloud to configure them correctly. Also, if you want to use a specific dedicated CNI plugin for your Kubernetes clusters, you might see also some problems. We experienced that one with Cilium, with a lot of configuration knobs. Another lesson learned during our development phase was that debugging network to debug networking in cloud, you need special tools, and you need to change your minds because or your approach, because not all regular tools are available, and not all regular tools work as they work on your local machine. In cloud providers, they limit your options. Moreover, with Cilium, we've seen some problems on the way. Some of them have been already fixed, but not all of them. So all those new tools, frameworks, features, they need to be tested very extensively. And you need to remember that a full with a tool is only a full, so you need to know your tools, you need to test, and you need to take your decision based on data, just to know what to expect in the future. So thank you very much. I think that we are running out of time, so I'm not sure if you have any time for questions. If not, reach me on Twitter. I'd be happy to answer all your questions there. Thank you.